No cables, no towers, just satellites beaming internet from space. From remote villages to stormy seas, satellite internet is rewriting the rules of global connectivity. But how does it actually work? What makes a system like Starlink so different from its predecessors? And how are other providers competing in this new orbital race? Today, we break down the technology, the strategy, and the future of internet from above. Satellite internet isn't a new concept, but for decades it was a solution of last resort plagued by significant limitations. Traditional satellite internet providers, such as HughesNet and Viasat, rely on a small number of very large satellites placed in geostationary orbit, or GEO. This orbit is located at a precise altitude of approximately 35,786 kilometers, or about 22,236 miles, directly above the Earth's equator. At this height, a satellite's orbital period matches the Earth's rotation, causing it to appear stationary from the ground. This allows a single satellite to provide continuous coverage over a vast geographical area, roughly one-third of the planet's surface. While this architecture simplifies ground antenna pointing, its greatest drawback is baked into the laws of physics: latency. Latency is the time it takes for a data signal to travel from your computer to a server and back. For a GEO satellite, this round trip is a journey of over 140,000 kilometers. Even at the speed of light, this distance introduces a minimum delay of 500 to 700 milliseconds, and often much more. This high latency makes real-time applications like video conferencing, online gaming, and even fast-paced web browsing feel sluggish and unresponsive. Furthermore, because the signal from a single GEO satellite is shared among many users across a wide area, bandwidth is often limited, leading to slower download and upload speeds, especially during peak usage times. For years, this was the accepted trade-off for getting online in places where terrestrial infrastructure was non-existent. This is where Starlink and the broader concept of low Earth orbit LEO constellations enters the picture, fundamentally changing the equation. Instead of a few large satellites far away, Starlink deploys a massive fleet of constellation of thousands of smaller, standardized satellites in low Earth orbit, typically at an altitude of around 550 kilometers. As of early 2024, SpaceX has launched over 6,000 Starlink satellites, creating a dense, interconnected mesh that blankets the globe. This proximity to Earth is the key to solving the latency problem. By dramatically shortening the signal's travel distance, LEO systems can achieve latencies as low as 25 to 50 milliseconds, comparable to and sometimes even better than ground-based fiber or cable internet. This low latency unlocks the full potential of the modern internet, making real-time applications seamless and responsive for users anywhere on the planet. Visualizing the Starlink constellation reveals a dynamic, constantly moving grid. Satellites race across the sky at incredible speeds, completing an orbit in about 95 minutes. A user on the ground is never connected to just one satellite for long. Their terminals seamlessly hands off the connection from one satellite to the next as they pass overhead. This architecture ensures continuous, uninterrupted service. Real-time coverage maps show this intricate celestial dance, a web of connectivity that is constantly in motion, providing coverage to nearly every corner of the Earth, from the highest mountains to the most remote oceans. The sheer scale is unprecedented. Starlink's operational satellite count now dwarfs the total number of all other active satellites combined, representing a paradigm shift in how we utilize near-Earth space. So, how does the signal actually get from a server farm in a major city to your laptop in the middle of nowhere? The process involves a sophisticated chain of communication. First, data travels from the global internet backbone to a ground station, also known as a gateway. These gateways are strategically positioned around the world and are connected to high-speed fiber optic networks. The ground station uses a large antenna to transmit the data up to a Starlink satellite currently passing overhead. This uplink and downlink communication primarily uses high-frequency radio waves in the Ku-band and Ka-band. What makes this possible is one of Starlink's core innovations, the use of phased array antennas on both the satellites and the user terminals. Unlike a traditional dish that must physically move to point at a satellite, a phased array antenna steers its radio beam electronically without any moving parts. This allows for near-instantaneous tracking of the fast-moving LEO satellites. Once the data is aboard a satellite, another revolutionary piece of technology comes into play: optical intersatellite links, or space lasers. Many of the newer generation Starlink satellites can communicate directly with each other using highly focused laser beams. This creates a resilient, high-bandwidth data network in space, allowing information to be routed between satellites at the speed of light without needing to return to a ground station. For example, a user in the middle of the Pacific Ocean could send data up to a satellite, which then relays it across a chain of other satellites via laser links before downlinking it to a ground station near its final destination in Europe. This space-based backhaul further reduces latency and increases the system's flexibility, as it lessens the dependence on having a ground station within the footprint of every satellite. Finally, the signal is beamed down to the user's terminal, a compact, self-aligning phased array dish affectionately nicknamed Dishy McDishface. This terminal automatically finds the optimal satellite in the sky and maintains a stable connection, delivering high-speed internet directly to the user's router. The result is a system capable of delivering speeds that were once unthinkable for satellite internet, with standard plans offering 100 to 200 megabits per second and premium tiers promising up to 500 Mbps. Starlink may be the most prominent, but it is by no means the only player in the LEO satellite internet race. A host of well-funded competitors are deploying their own constellations, each with a slightly different strategy. OneWeb, now majority owned by the French satellite operator Eutelsat, was one of the earliest contenders. Its constellation operates at a higher LEO altitude of about 1,200 kilometers and uses a different frequency band. OneWeb has primarily focused on enterprise and government markets, including aviation and cellular backhaul, rather than direct-to-consumer services. Its satellites are also in a near-polar orbit, which provides excellent and consistent coverage of the Arctic and Antarctic regions, a key strategic advantage for shipping and scientific research. Then there is Amazon's Project Kuiper, a formidable competitor backed by one of the world's largest technology companies. Kuiper plans to deploy over 3,200 satellites and has secured massive launch contracts, including with its sister company, Blue Origin. While Kuiper's overall architecture is similar to Starlink's, it aims to differentiate itself by leveraging Amazon's massive cloud infrastructure and its global logistics network to streamline operations and service delivery. Other players, like Canada's Telesat with its Lightspeed network, are also targeting the enterprise market with advanced architectures designed for high-security, low-latency corporate and government communications. This growing competition is fostering innovation and driving down costs, but it's also fueling concerns about the sustainability of the space environment. Indeed, the rapid expansion of these mega-constellations is not without significant challenges. The most immediate concern is orbital congestion and the rising risk of space debris. With tens of thousands of new satellites planned for launch in the coming decade, the orbital highways are becoming increasingly crowded. A collision between two satellites could generate a cloud of thousands of pieces of high-velocity debris, each capable of destroying other satellites and setting off a chain reaction known as the Kessler syndrome, which could render certain orbits unusable for generations. Satellite operators are developing automated collision avoidance systems, but the sheer number of objects makes tracking and management a monumental task. Furthermore, these constellations face regulatory hurdles. Every satellite must be licensed, and the radio frequencies they use must be allocated and coordinated internationally to avoid interference. This process is managed by global bodies like the International Telecommunication Union (ITU) and national regulators like the U.S. Federal Communications Commission (FCC). As more companies vie for the same limited spectrum and orbital slots, regulatory battles are becoming more frequent and complex. Finally, there are physical limitations. Heavy rain, snow, or even dense cloud cover can absorb and scatter the high-frequency radio signals used by satellite systems, a phenomenon known as rain fade, which can temporarily degrade or interrupt service. While modern systems have built-in margins to mitigate this, it remains a fundamental challenge of atmospheric physics. Looking forward, the evolution of satellite connectivity is set to accelerate. Starlink is already deploying its VIDA satellites, which are larger, more powerful, and equipped with advanced 200 Gbps laser links that will dramatically increase the capacity of the in-space network. The next frontier is direct-to-cell service, where standard smartphones can connect directly to satellites for basic messaging and emergency services, effectively eliminating cellular dead zones worldwide. This technology is already being integrated into new vehicles, aircraft, and maritime vessels, providing redundant, high-speed connectivity for safety and operational efficiency. In disaster zones, where ground infrastructure is often the first thing to fail, satellite terminals can be deployed in minutes to restore critical communication lines for first responders and affected communities. We are witnessing the fusion of space technology and telecommunications on a global scale. The sky is no longer the limit, it's the network.